Hi, the next data structure is hashing. So we have been learning many data structures, and hashing is another type of data structure with a special purpose. Okay, especially, for example, if you want to build up a dictionary, okay, a Korean English dictionary, then you can think of some other data structures like a BST. Okay, but in this case, hashing would be a better solution, a better data structure. And if you want to build up a phone book with lots of friends, lots of people in there, then hash table would be a better data structure. Okay, so let's talk about hashing. First, we're going to talk about symbol table as an abstract data type first, and then in this section, we're going to talk about the motivation of hashing. Okay, and what's the benefit of using hashing table. Okay, we'll talk about that. And then there are two basic approaches. First one is the static hashing, and second is dynamic hashing. As you know, in computer science, static means it's not changing. Okay, so once the hash table is fixed, then we don't change it. And dynamic hashing means dynamically we change the hash table. So dynamic hashing might be more complicated to implement, but it's more flexible, right? So we'll talk about these two approaches. Okay, first one, a symbol table. And symbol table is a set of name attribute pairs. So attribute could be anything. It depends on the applications. We already talked about these name attribute pairs before, like C+ standard template library includes map. Okay, so map has a key and value. Likewise, we have a name and attribute pair. Okay, and then attribute could be anything, as I said. If it is a dictionary, then name is a word and attribute is the description of that word. Okay, that is attribute of dictionary. And if it is a thesaurus, then the name would be a word and the attribute would be a set of similar words. What about the phone book? In that case, the name is the person's name and the attribute includes phone number and email address and some extra information. Okay, so we have a name and attribute pairs for some applications, and these pairs could be different depending on the application. Okay, let's define this as an abstract data type. First, object is a set of name attribute pairs where names are unique. This is another important part. Names should be unique. Think about a dictionary. And sometimes one word might have a couple of different meanings, but still, we need just one unique word, including lots of meanings. And think about the phone books. Sometimes we might have a couple of different friends with the same name accidentally, but still we need different name for them. If we have two Henry Kim, then probably we need something like a Henry Kim A, Henry Kim B. Okay, whatever it is, we need a unique name for our phone book. Okay, then in this abstract data type, we have a couple of operations. First one is a create. Obviously, create will make an empty symbol table, and as a parameter, we can get the max size. So this defines the size of hash table. And the next operation is kind of brand new operation. We've never seen this kind of operation before with other data structures. Is in. Is in means we want to check if this name is in the symbol table. For example, let's assume that we have a dictionary. Okay, and then as I said, the names are the words and the attributes are the explanation or description of the word. Okay, then is in function is checking if one specific word is actually in the dictionary. So when we have one word, then we might not be sure about this word. Then we want to ask if this word is in the dictionary. It means if this word is valid word. Okay, or does it include some typos in it? So to check if this word is valid, then we want to make sure that this word is from the dictionary. So is it in the dictionary? So this function is checking if this name is in the symbol table. If it is, then it returns true, otherwise it returns false. And next function is find. Find is going to return the corresponding attribute. So basically, we search. We want to check if there is this name in the dictionary, and if it is, then it will return the attribute. So there is a difference between the is-in and find. Is-in will return the true and false, but find will return attribute or null. Okay, that's the difference between is-in and find. But basically, these two functions are based on the search. Okay, and then the next operation is insert, and then the last one is delete. Okay, remember the hash table, symbol table is actually a data structure. And if it is data structure, then the search and insert and delete, these operations are kind of fundamental operations. We should be able to insert something, and we should be able to delete something from the data structure, and we should be able to search, right? So these are kind of fundamental operations. Okay, as I said a moment ago, we have three basic operations: searching, inserting, and deleting. Okay, good. And now let's talk about the actual implementation or representations. Okay, how can we represent our symbol table? Okay, and binary search tree would be one good candidate. Actually, we use these binary search trees. In a node, then we can have a key and the value. And this binary tree would work based on the keys. Okay, so we can search based on the key, and we can delete and we can insert based on the keys, and the attribute or data will follow the keys as a single node, right? So BSD is kind of one good candidate for the symbol table, to implement a symbol table. Good, but there is a problem here. If the binary search tree is not balanced, then it will take n times in the time complexity, big O notation, right? But if it is well balanced, like AVL tree or red-black tree, then log n would be enough to search. Okay, that's good. But is it the best options? Isn't there more efficient representation for this kind of specific data type? There is a better solutions. There is better representation, which is hashing. Okay, so as I said, we have static hashing and dynamic hashing. Okay, when search time matters, then hashing would be better than binary search tree. Okay, hashing would be able to find one specific key much faster than BST. So from now on, let's talk about static hashing. Okay, static hashing is based on the hash table, which is to store identifiers. Again, hash table will handle the identifiers. Okay, but we don't talk much about the attributes here, but remember, attributes are connected to these identifiers all the time. Okay, and in the static hashing, table size is fixed. Okay, and then we need a hash functions, which is a function from identifier to address or locations. Okay, what does that mean? So given an identifier, then hash function will find the location. It will transfer the identifier to address or locations. For example, we have an identifier here, and then the table size is fixed, which is B. So we have B buckets here from 0 to B minus 1. And given an identifier, then hash function will return a number which is between 0 and B minus 1. Okay, so when the identifier is X, then when f of X is 2, then the X will be located here. So given an X, then we can find where X is. Let's take an example of this. So we are interested in the dictionary, okay, and then we are looking for a word school, okay. Then we have to search. but not from the beginning, not from the end of the dictionary. Okay, and if we have some good hash functions, which tells us where the school is in the dictionary, so it returns the page number. If we have a perfect hash function which tells us the page of a specific word, then that's great. Then we can open the dictionary, and then in a specific page, then we can search our target word. We can search school from this page. So we don't have to look at all the other pages. Hash function will guide us to a specific page. That's great. If we don't have this kind of optimal hash function, but we'll talk about this hash function later. But if we have an optimal hash function, then that is great, right? So given a word, then it just shows us one page, and then from this page we can find our target word. And the beauty of this hash function is that we can find the page with constant time. This hash function doesn't have any kind of for loop. Okay, so we have identifier as a parameter, and the hash function will return a number, a page number. It doesn't matter how many words we have. Hash function doesn't care the other words. Okay, given this one word, one identifier, it returns a number, the location or address. In the dictionary, it returns the page. Okay, so since the hash function is working only with the identifier, so it can finish this job in a constant time. That's the beauty of this hash table. So given a word, it shows us one page in a constant time. And in the page, we have to search. Okay. So in this figure, this bucket corresponds to a page in the dictionary. Okay. So given a word, then it shows us the page number. And in the page, we have lots of words too. So we have 2 slots, or sometimes we have, in a dictionary, we can have like 30 words or 37 words in a single page. So in that case, we have 37 slots. Here is another good hashing example. So we have 10 identifiers here, and then we have a really simple hash function. Okay, so this is really tiny, simple hash functions. We don't use this kind of hash function in practice, but this function is for explanations. Okay, so this hash function is really simple, and we actually check the first character of these identifiers. Okay, and then we have 26 buckets. 26 means the number of alphabets. Okay, so we check the first character of the identifier, and we actually find the location of the words. For example, if it is a cosine, so the first character is a, then a corresponds to 0, so a cos is located in this slot. Good. And next, define. The first character is d, so d corresponds to 3 because d is the fourth character. Okay, so define is here. And the next, float. Float has f, and f is the 6th character, so float is here, is located. And then exp, okay, here. The next character, okay, here. Perfect. And the next one is a tangent, arctangent. So the first character is a. Okay, so a corresponds to 0. So a tangent should be in this bucket, right? And when we check the first slot, it is full. So there is someone already there, and a tangent should be in the second slot. Don't get me wrong, these are not sorted. Okay, even the second one is AAA, then still we have to have AAA here. Okay, so this one is not based on the sorting. Okay, not at all. And how about next one, seal? Seal has a C as first character, and the C is the third character, so it should be in this bucket. And the first slot is already checked, and the seal should be in the second slot. Okay, so this is simple, and this explains pretty much everything about hashing. So as I said, when we apply a hash function for like a define, and we don't care the other identifiers, only based on this identifier we can find the locations. Define should be here. Okay, so now let's assume that our hash table is kind of full with some empty cells. Okay, and we are looking for a specific word like A, B, C. Okay, so we are looking for A, B, C. Then we don't have to look at the other buckets. We can go to this first bucket directly. Okay, and if we have a void, then void is a little hard. Somewhere around here. Okay, so based on this first character, we know where it is, if there is. Okay, then we don't carry the other buckets. So when we search, it takes just constant time to get to a specific bucket. So that's why hashing table is so fast compared to other data structures. Think about the BST. In a BST, when we are searching, we have to check the first root node, and then depending on the result, if our key is smaller than the root node key, then we have to go to the left subtree, and then from the left subtree, then we have to do the same thing again and again recursively until we find the target node. Okay, so we have to follow this tree, but in the hashing table, there is nothing like a linked list. We'll talk about linked list later, but to get to the bucket, there is nothing like a linked list. We don't have to follow anything. We can go there directly with a constant time. Okay, so I'm emphasizing this thing again and again because that's why we use hash table. Okay, the next one is terminologies. It includes some notations. So first, let's define some variables. B is the number of buckets in the hash table. S is the number of slots per bucket. Okay, so we know them. And the T is the number of possible identifiers. What does that mean? So for example, if we limit the length of identifiers to 6 characters where the first characters are alphabet, then the T is 26 times 26 plus 10. 26 is for the number of alphabet characters, and 26 plus 10 means alphanumeric characters. Okay, so if our identifiers have 6 characters, then this is the possible number of identifiers. So T is actually the possible number of words if you think about the dictionary. Okay, all the different kind of combinations could be considered here. Okay, then so what is the N here? N is the number of identifiers in the table, so actual identifiers. So let's go back to the dictionary analogy. Okay, in the dictionary, T is all the kind of potentially possible combination of the characters. Okay, but N is actual the number of words in our dictionary, like 22,000 words in our dictionary or so. And so usually N is way much smaller than T. And we have some other variables to indicate some properties of our hash table. So first one is identifier density, which is N over T. So N is the number of actual identifier and T is the number of potential identifiers. Okay, and the next one is a loading density or a loading factor, which is alpha, which is N over S times B. So S times B is the size of hash table. Okay, so B is the number of buckets and S is the number of slots. So if S is 3 and the number of bucket is 4, then we have 12 kind of slots in our hash table. Then when we have 4 identifiers, then 4 over 12. That's alpha. Okay, then the alpha is higher than a threshold, like if we have lots of cells with identifiers, then it's too dense. Then it will have some problems in future when we need to insert new identifiers. So we have to do some things when this alpha is high, too high. And there are synonyms, which are the identifiers with the same hash function outputs. So in the previous example, a cosine and a tangent, these two identifiers are synonyms based on that hash function. Okay, if our hash function is based on the second character, these two are not synonyms. So if we change our hash function, then the synonyms will be different. And the next one is overflow. Overflow occurs when we hash a new identifier I into a full bucket. So for example, in this case, this bucket is full. So we already have 3 identifiers in this bucket when the slot size is 3. In that case, if we insert another identifier which belongs to this bucket, then it is full already, so there is overflow. Then we have to handle these kind of situations. We'll talk about it later. And the next one is collision. Collision occurs when we hash 2 non-identical identifiers into the same bucket. So collision and overflow, these two are slightly different. So when we insert a new identifier here, okay, then there is something in this bucket, then there is collision, okay, but there is no overflow. But if we insert something into this bucket one more time, then we have a collision and overflow. So to have an overflow, then we will have a collision first, and then we'll have overflow. This slide explains the variables n, t, b, and the loading density. Okay, so it explains overflow and collisions, etc. We have the same example as before, and the hash function is the same as before. And when we insert a new one, like a clock, then we have a collision, and then we have overflow. And then if we insert the C time, then we have collision and overflow one more time. Okay. So now, let's check the variables. How many identifiers do we have? 10 identifiers, so n is 10. And what is t? These identifiers could be identifiers in program language. Okay, so it starts with alphabet character, but it will include alphanumeric characters in the middle of the identifier. So let's assume that the length is 6. Then the t would be this number. Okay, this is huge. And b is 26, and s is 2. Then let's check the loading factor. Alpha is 10 over 26 times 2. So 10 is the number of identifier, and 26 times 2 is the size of our hash table, which is 0.19, which is smaller than 0.75, which is a predefined threshold. If alpha is larger than 0.75 or any predefined threshold, then we have to expand our hash table for the future insertions. Okay. And in this example, a cosine and a tangent are synonyms, as are float and floor, and so on. Okay, so analysis. Without the collision or overflow, let's assume that our hash table is perfect, optimal. So we don't have any problem with the collision or overflow. Then the complexity of insertion, deletion, or search is just constant time. They are done in a constant time. As I said, all these operations are based on just the identifier. Okay, so we don't care the other identifiers at all for these operations, so that it could be just constant time. It has nothing to do with other identifiers. Again, if you think about the BST, when we insert a new key into a BST, then we have to check the other identifier, the other keys. So we have to check the root key, and then depending on the value, then probably we might have to check the left subtree's root key or right subtree's root key, and etc. Recursively, we have to check the other keys. So that's why the best algorithm would take log n. Okay, even with the well-balanced tree. But with hash table, since we don't care the other identifiers at all when we insert, delete, or search, so just constant time. But there is no free lunch. Okay, it comes at a cost, which is not cheap. Okay, major issues in hashing has two problems. So first one, the choice of hash function. In previous examples, we had really simple hash functions. It takes just first character, but that is not a good choice, okay? And if it is a good hash function, then we need less number of collisions and less number of overflows. And also, this function should be easy. Even though this is constant time, but still, we need easy computations for a hash function. Even though it is constant, but still, in practice, constant matters sometimes. So each computation is another important factor. And the next issue is handling overflow. Okay, even with a really good hash function, but still there will be overflow. Overflow is inevitable. So when n over sb becomes large, then it's really hard to avoid collisions and overflows. So as n increases, then in our hash table, all the slots will be full. Then somehow, eventually, we are going to get overflow problem. So we are going to meet the overflow problem eventually. Then what should we do? Even with the perfect hash function, we're going to get overflow problem. Then we have to handle that. We have to deal with it, right? So our hash function, hash table should be able to handle this kind of problems.